let us first do attendance. Boop. So please tell me that you exist. And then today we will talk about some new topics, and I want to remember to tell you about your final because we are in week 15. There are 17 weeks of classes, and then week 18 is the finals week. So don't let me let you leave without talking about the final, okay? All right, so let's go back to these slides. Because of all the holidays in this class, I had to shift stuff around. Normally we would have finished these long ago, but I had to give programming stuff first so that you could do your next assignments, your next programming assignments. But remember these slides? We were talking about computer science and medicine, science, art even. Cool stuff. So let's talk about computer science and finance. It would not be a computer science class if I did not talk about cryptocurrency. So let's make that happen. Okay? Let's have fun. And maybe there are plenty of you that know more about it than me. Please shout out. Let's make this a conversation. So let's talk about Bitcoin, because that's the most popular one still, right? Ethereum is getting popular too, but I think Bitcoin still reigns supreme. So let's talk about what Bitcoin is all about, how it works, and what's going on with it. So it's definitely the most popular cryptocurrency, right? And I am not going to get into the nitty-gritty details, but we can if you'd like to. Maybe I'm not qualified enough, but I know a little bit. So I'll just be talking about it at a high level, not like we're trying to implement the Bitcoin protocol. But let's just talk about it in general, okay? So a cryptocurrency, it is some type of virtual money, right? It's completely electronic. It's money that's completely electronic. We don't have any bills to give out. It's all over the wires, okay? And the way that we know who has what is with encryption, all this kind of stuff that we've been talking about before, public, private keys, things like that. That is the way we know whose bank account has how much Bitcoin, okay? So all that stuff that we know about is really making good use here. So through encryption, I can have a Bitcoin account. And through encryption, my cat can also have a Bitcoin account. And maybe I can transfer money from myself to my cat. And there's some properties. You remember RSA, that kind of public-private key stuff that lets the Bitcoin protocol know that I'm taking away some of my money. It goes away, and then it's going into somebody else's account. And that's how it all works. We're passing information. This is all just ones and zeros at the end of the day. Okay? And Bitcoin was created. It was the first cryptocurrency. It was made back in 2009 by somebody who calls themselves Satoshi Nakamoto, which is supposedly a pseudonym. That's not anybody's real name, and they're still in hiding, right? I don't think anybody has really come out to be Satoshi yet. Is that still true? I haven't been following that too closely, but I feel like there are some people who are pointing fingers, but nobody's been like, yeah, it was me. But people have ideas. So yeah, cryptocurrencies, because they're based around these kinds of encryption protocols that we've been talking about, they are naturally very hard to track, right? You have to, you can buy Bitcoin, and assuming you buy it not in the US, and you sell it to somebody, and you make money in another cryptocurrency, you don't, the IRS is never going to figure that out. So you're forced to tell them, and I mean, you're supposed to, but it's really hard to track it. And that's kind of the point. That was the point of cryptocurrency. Nobody knows what's going where until you finally cash out and convert it back to dollars or something. Okay? And Bitcoin started it all. There are now a bunch of alternative Bitcoins or altcoins that have been created, like Ethereum and Litcoin and all these fancy things made about memes as well. But I think Bitcoin is still the most lucrative. One Bitcoin is some amount of money, and I have it on a future slide. It's 45-ish thousand right now for a single Bitcoin. So there's a concept of a Bitcoin wallet, how much money you have. And there's also a concept of a Bitcoin address. That is where my money lives. That's my account number, essentially. Okay, any questions about this high-level idea stuff before I get into slightly lower-level things, like how money's moving around? More terms. And I have a fun activity for us later if you participate. I think it will be fun. So let's talk about the blockchain now. That's another key term about Bitcoin. So what is Bitcoin but a bunch of computers on the same network? It's kind of like peer-to-peer file sharing all over again. It's just money sharing, I guess. Okay? So it's a peer-to-peer network. Computers working together, talking together. It's all based around encryption. That's making it easy to figure out where to put things and making it sure that nobody else can steal my own money. So everybody has an account number, and that is their public key. Okay, that's your public key. Remember the difference? That's something that you give to everybody. They can talk to you that way. And then, if you want to give money to somebody else, you can't use that account associated with that public key without a corresponding private key, right? That's what makes it all go around, and that's the one you don't give to anybody. That's the one you hide, okay? So, yeah, essentially, there are a bunch of computers talking to each other. I don't know. Here's my laptop. Maybe it's on the Bitcoin protocol. I don't think the school wants me to be. And then it's talking to a bunch of other computers on the Bitcoin network. It's like, here's what I think the state of every Bitcoin in the universe looks like. And they're all talking to each other. There's a nice web of computers. And what they all are storing, what they're all talking to each other with, is this thing called the blockchain. It's just a really big file, okay? It's a file that has said every single transaction that has ever happened on Bitcoin. So everybody has a copy of this thing called the blockchain. It's like money existed, and Lawton gave money to his cat gave him some money back. Every single transaction between every single pair of people, that is the blockchain. That is what everybody is trying to store on their own ends, a copy of this. And hopefully they all agree on who got what money when. That is the hard part. That's what Bitcoin tries to solve. Because then everybody who is on the network knows the contents of everybody else's account. And there's no contention. Everybody agrees. That's the idea. Okay, so the blockchain records every single transaction that has taken place since the beginning of Bitcoin. And if you read it from the start, you would know exactly how much money is in what account. That's the idea. And so everybody has a copy, and maybe I have my own local copy, and like this is my account. I have what I think my account is. I have my own copy of the blockchain. Here's all my Bitcoins. And if I want to send money, I like sign it with my private key, and everybody sends money to my public key. That is how it's working. So yeah, if somebody wants to spend money, everybody's blockchain gets a copy of that new transaction. So I'm sending some money onto the network to somebody else. I'm sending money to my cat. That means I am broadcasting that information out to all these interconnected computers so that they can all say, oh yes, Lawton spent money, he has fewer Bitcoins in his account, and now somebody else has more. Okay? Are there any questions about that process? That's essentially what's going on. The hard part is the thing I'm glossing over, how to get everybody to agree on the contents of this giant file called the blockchain. Because maybe I want to fake that my account has 1 million Bitcoin in it on my little local copy of the blockchain. How does everybody else realize that no, that was not right? No, he's lying. So there's some very fancy things going on there that I don't have time to get into, but this is like a high-level idea of it. Any questions about that? Yeah, so the blockchain is just every transaction for every account from the start of time to today. And everybody's forced to agree. Okay, so yeah, let's talk about that idea of lying on the Bitcoin network. Because if you're a bad person, or you want more money, you would, to your local copy of the blockchain, you would say, oh yes, my account just got 1,000 Bitcoins. That is the truth. Okay, you'd try to write that to the blockchain, wouldn't you? All these interconnected computers would be like, let me think about that. Okay? So everybody is connected to everybody else, and that is where we get strength in numbers. That is how you can get around this issue of a single malicious user. Okay? So you can try to do this, but the network is going to disagree with you. Okay? The idea is that when you send out a transaction, you need a majority vote for everybody who's connected to the network at the time to say, oh yes, this transaction is going through. It's happening. Okay? That is the secret. So greater than 50% of the computers, a real majority, have to agree to make sure that a transaction takes place. Otherwise, it gets rolled back and it doesn't happen. Okay? So you on your own end trying to say, I would like to get 1,000 Bitcoins, and maybe you have like 3 computers all connected to the network, all trying to agree with that. Well, the rest of the network is huge, right? And they're not going to agree with you. So that is going to stall your dreams to steal Bitcoins, unfortunately. Okay? But this does pose an issue. If somehow you were some kind of entity that had a ridiculous amount of computing power, think large governments, you could technically make Bitcoin not work anymore, right? Because if you had 50% of the computers connected to the internet, plus one more, right? Connected to the Bitcoin network, plus one more, you could then write some silly things to the blockchain, and then, well, you have a majority. Everybody has to agree with you. That's kind of interesting. How do we feel about that? Have we thought about that before? Have you heard this idea of majority? It's a little weird. And so luckily, Bitcoin is so large, everybody's talking to everybody. There's a lot of computers on the network, so you can't really have this kind of issue these days. But some of those alternative cryptocurrencies have had this happen to them because there aren't a lot of people connected on that particular network. So that is an issue. Okay? So that is majority rule. Any questions before I move on to, I guess, one last topic about Bitcoin, and then we'll analyze it. All right. So let's talk about mining, because maybe we've heard that term. That's kind of the last term that I want to talk to you about. Okay? So let's talk about what mining means. Because everybody wants to mine Bitcoins. You have to, this is the reason graphics cards are so expensive these days. This is affecting us, even though maybe we're not caring too much about Bitcoin. So what in the world is mining? It is how money gets made on the Bitcoin network. That's how it works. Okay? So mining is essentially an incentive for people to put their computers on the network and store this giant copy of the blockchain. That takes energy and storage. Why would you want to do that? And the reason is mining. Okay? To get people to do this, to interconnect their computers together like this, every time you have a few transactions, I forget the exact number, but every time a few transactions take place on the network and everybody agrees, then there is a secret special lottery that happens where money gets made out of thin air. That's how Bitcoins get created, okay? So everybody who's trying to coordinate on these transactions saying, yes, I agree, yes, it makes sense, this is fine, all of those people talking to each other, they are eligible to win this lottery, okay? So one lucky participant gets a little bit of Bitcoin. I forget the amount now. It's I don't know, is it 1 Bitcoin, maybe half a Bitcoin these days? I'm not sure. But just for putting a check mark next to that transaction, they get Bitcoin, okay? And that's essentially how Bitcoin gets made. Because at the very beginning of time, there was no Bitcoin, but then we had a transaction and people were mining things. Those participants who were storing their blockchain, they got a copy of a Bitcoin. Okay? That is how it's working. And so, let me try and teach you what needs to happen in order to mine a Bitcoin block. So, First of all, there was a lot of Bitcoin being given to people for verifying these transactions at the start of the life of Bitcoin. But it's programmed to give out less and less money in this lottery over time. That's the first thing. And eventually it's going to stop. Eventually no more money gets printed whenever transactions get verified. And the lottery is this. The lottery is, okay, take every of those new transactions and compute a very special number called a hash based on them. Maybe we've heard that number, that word before. And then the trick is to find a winning number. So take that information from these transactions and manipulate it in a standard way. And I would like to see a certain number of zeros at the start of that fancy number that we're computing based on these transactions. This is the technical process of mining. And the first person who can find a number that gives you a bunch of zeros when you jumble all of these transactions together in a special way, they get the Bitcoin. They get that, they win the lottery, they have mined something, okay? That's how it works. And so everybody who's on the network is fighting for this. They're trying to hash these numbers very quickly to get a bunch of zeros at the start, and whoever wins gets that block. We say that they have mined that block of Bitcoin, okay? They verified the transaction fast enough in that super secret special way. And that is mining in a nutshell. Are there any questions about this process? So it's just like computers solving a hard math problem, essentially. And that's what creates Bitcoin. That's fun. So we wouldn't be in this class if we stopped there, right? Let's talk about what is this? How is this fine? Should we have cryptocurrency? What does this mean for us? Okay. First of all, I like to every semester keep track of the current price of Bitcoin. So at the start, the first time I taught this class, Bitcoin was at like 11,000. Second semester, it was at like 60,000. Then it was at 66, and now it's back down to 45. So it's all over the place. This is the most recent one right now. So that's fun. But let's try and analyze this, okay? So is this fine? Should we have cryptocurrency? Is this okay? What is good about it? What is bad about it? At least that's what we can do in terms of utilitarianism. Let's go back to our boys. Let's remember them, okay? So one con about Bitcoin is, it was so decentralized. Anybody can use it. You don't have to associate your name with your account. You can just keep spending on the network and nobody knows who's getting what. So the first real uses of Bitcoin, therefore, were for things that people didn't want to attach their name to. For black markets, buying drugs, things like that. Those were the first uses of Bitcoin. So maybe cryptocurrency in general is bad because of that. But nowadays, it's like people are actually spending Bitcoins on real things. A lot of like online stores these days, they take cryptocurrency, which is weird to even think about. But so maybe this held some weight at the start, but maybe not anymore. Okay, so we have to deal with what it means now. Another bad thing about that anonymity is that your government can't track who owns what money to tax you, who's spending what money, what's going where. Because, again, you can be buying bad things. You could be buying off politicians, I guess, with Bitcoin if you wanted to. So because of that, is that a problem? Or maybe that's a great thing. Like, we should have freedom of speech, freedom of money transfer. Our government shouldn't be involved in that. What do we think about this? Any comments, questions? Do we think cryptocurrency is a good thing in general? And then it's a question of maybe we don't like Bitcoin, but maybe we like something else for certain reasons, okay? Also, as these pictures on the right tell you, the exchange rate of Bitcoin, like 1 Bitcoin to how much US dollars, you have no guarantees about it. Like it got up really high, and then now it's back down. Maybe one day it's going to be even lower or even higher. We're not sure. It's like stocks. So there's no real guarantees in how much money you're going to get a year from now if you own a Bitcoin. Nobody knows. And partially, the reason for that is that no governments are backing Bitcoin. Actually, I think I think a South American country is actually starting to use Bitcoin. Is that right? Do we remember which one? I can't. So maybe this is, I should say most. Almost all. True. That is true. But no government is buying another government's debt in Bitcoin, for example. That comes with some guarantees when people do that, though. And so that's kind of what I'm trying to say there. Nobody has any confidence that, like, this is going to be worth anything. But when people buy dollars, they're pretty confident that that's going to mean something a year from now. Like, the US dollar isn't going to collapse. So there is a back and forth there. Who knows? Maybe it's useful, maybe it's not. Yeah. Any other comments? This is a good discussion, I think. Because we can always ask our boys, and that's what I'll do next. All right, so let's ask Kant, for example. What would Kant say about cryptocurrency, Bitcoin, things like that? I think we've established that Kant is for individual rights, right? He's for people doing whatever they want if they're not hurting anybody. And he would say, yeah, cryptocurrency is great. We should have that as an option because we can expect the good in people, right? We can assume that people are going to pay their taxes based on selling Bitcoins. They're not going to lie to their governments, things like that. Kant is an optimist, okay? So I think Kant would be for cryptocurrency. And usually for Mill, you can go either way depending on how you argue it. So that's why it's fun to talk about him too. Yes? Question.
Did you hear that El Salvador's leader made Bitcoin legal tender?
Okay, was that the country, El Salvador?
Yeah.
Okay, nice. Thank you. Yeah, so that's useful. Maybe for a country who doesn't have like a strong currency. Maybe Bitcoin has some better guarantees than that particular currency, and that's the reason they're going with it. So there are arguments in favor, and we have to consider those. All right. Yeah, so let's go back to Mill. That's a great point there. So yeah, from a government's point of view, let's say, I think that cryptocurrency is probably a bad thing to most governments. Like, I can't track this. I want to know about people, like citizens, spending their money. If I were a government, maybe that's what I would think, right? And that gives them less tax money because people are not, like, I don't know what you do on your taxes, like declaring that you sold some stuff. You have more illicit activity because of this anonymity. People buying drugs easier because Bitcoin doesn't say who the money is attached to. There's also, and we haven't got into this yet, there's a huge environmental cost for Bitcoin specifically. Other cryptocurrencies sometimes don't have this problem, but Bitcoin, like, everybody wants to mine Bitcoin, and I think what's the term that they used? I read an article that said that the amount of energy spent to mine Bitcoin each year is the equivalent of the energy usage of Argentina. Something like that. Just for Bitcoin. So we're wasting a ton of energy because people want to get rich. Is that worth it? That's, depending on how your energy is getting created, that's burning fossil fuels, right? That is an environmental issue now, to have Bitcoin in the world. So that's very interesting to think about. That's another con, isn't it? That is weird, but a thing. And then you do have the flip side, though. So it's great for individual freedoms. Like, you don't have to attach your name to your money. It's perfect. You don't have to be tracked as easily. It's hard to track you when you just have a Bitcoin address. That's awesome, okay? And so maybe that's the reason it's a good thing. And it's up to you as the essay writer to say, like, okay, this is better than this. I've weighed these options, and this one comes out on top. Are there any questions, more comments about this stuff? This is a fun topic because it's relevant, and I think we've all heard about it at least. So it's fun to talk about. Yeah.
Aren't like computers just like generically horribly with energy? Like, they're so inefficient.
That's a good point. I'm not I'm not sure how true that is. I know back in the day, like, computers took up a giant room, and they were horrible, even worse than now. But I guess I have a laptop sitting in front of me. It can last for the day. It's not, I guess it's all relative, is what I want to say.
They're not laptops.
Oh, yeah. If we're talking about Bitcoin mining rigs, yeah, then they just waste a lot of energy because they're trying to do computation as fast as humanly possible. And to speed up, like to overclock a CPU, it requires more energy, right? So that is because it's got to work harder. It's got to burn more electricity, which is like, think of that as gas, I guess. So that's a great point. Yeah, that's the reason. If you wanna win the mining lottery, then you need the fastest computer, and that is going to waste extra energy. Very good point. Yeah. Any other comments about this? Because I have a fun activity for us if we would like to play. I do this every semester. So I'm going to introduce our class's own cryptocurrency. I will call it Litcoin, because why not? It's going to go to the moon. And I can't give you any real money for it, but I'm going to give you the opportunity to mine a Litcoin right now. Okay? I will make my own as you're doing this, but here is the game. So you can mine a Litcoin if you would like by solving a math problem the fastest, because that's essentially what a computer is doing when it's mining Bitcoin. Okay? So I have some questions on the next slide, and let me write a spot for you. Here's a marker. The first person to answer one of these questions correctly, put your answer next to it. Oh, this is a horrible marker. Of course you are. This is 1, 2, 3. That's better. 1, 2, 3. Let's just make sure this one works before I give it to you. Yeah, this one's fine. So the first person to write the answer associated with this number on the board gets a Litcoin. I'm going to like write them on a piece of paper right now for you, so I can give you something physical. It will be on napkins. But are we ready? There are 3 questions total. Each person who gets the answer right first gets the Litcoin. Okay? Ready, set, go. Here are your questions. And this is what computers are doing billions of times a second. You get to experience it. And I will verify your answer. So if you think you have the right answer and it, like somebody's already written it, and it's not the same, go write it next to it. How fast can we Google? Google does have a calculator in it too. That's useful. Oh, I need to look up the answer for the weather question, don't I? All right. I think the more accurate answer is the answer, I would say. Are we all confident with these? It's a very precise question to ask. All right. So my answer for number 1, at least the one that I have saved before, we're all done trying, right? Here's my answer to number 1. Are you ready to look at them? So here's apparently the answer to number 1. 1, 2, 5, 9, 1, 2, 8. I feel like that is correct if you do that times 10. So who wrote the more precise answer for number 1? Very nice. And then the next one, atomic mass of carbon times atomic mass of sulfur in those atomic mass units, whatever you call them. 385.07-ish. That's close enough. Depends on which isotopes you're using. Who wrote that one? Very nice. You have mined the Litcoin. Now, you can now sell it to somebody else, and then we can have some sort of conversion factor to dollars. And then today's max temperature in Celsius was apparently 26 in Fresno, and then San Francisco's max temperature today in Fahrenheit was 60 that I looked up. So the answer is supposed to be 86. But I guess nobody else tried, so whoever wrote that one came up.
I misread the first one as Fahrenheit for some reason.
You need a faster mining rig. That's essentially Bitcoin mining in a nutshell. So thank you for participating. All right. Yeah, any last questions before I go to a brand new topic? That is finance in computer science. All right. The next topic that I like to go into is game theory, which is quite fun. Let's talk about that. That is a nice combination of mathematics, computer science, economics, very weird things going on here. And I would like to teach it to you. Because of that, it's interdisciplinary. So let's talk about game theory. Maybe we've heard this before. It's fun to study. Let me give you a sneak peek at it, just in case you learn about it later for your respective major. So, I don't know, this is Fresno. So my example involves two people who have grown some corn, two corn farmers or producers. And the question, the age-old question, two different people competing, how much money should these corn farmers sell their corn for? They each open up a stand, and they put a dollar amount on their stand. You got your stand A, person selling corn at, and then you have your stand B, person selling corn at that one. Okay? They're both standing next to their stands, of course. Okay, so this is just economics at this point. If somebody sells their corn for very cheap, like person B is asking for $3.50 for an ear of corn, and person A is like, oh no, I have high-grade organic grass-fed corn for $50, everybody's going to go, for the most part, to person B, right? And they're going to make the most money. So if one sells high, the other sells low, everybody's going to go to the cheap one, except the people who want to show off, right? That is what's going to happen. And then game theory is going to tell us that person A will most likely lower their prices. That's the idea, okay? It will drive down the prices for the same product from the more expensive producer. And what game theory is very good at is telling us where the equilibrium lies, okay? That's the idea. So person A is probably going to come down to $3.50, the price at which they can compete the easiest with person B. Maybe they'll even lower their price. Who knows? And then maybe person B will lower theirs, and it's just a game. But there will be some tug and pull, but for the most part, they're going to settle around a certain price. That's how it's going to work. Okay, so that's called equilibrium. That is a very, very key word in game theory. This is all true unless they do something illegal. If they collude on the price, then they can both set the price to 50, and everybody has to spend $1 million for corn. That's totally possible. Okay, but luckily that is illegal, at least in the U.S. right now. So game theory will tell us the trustworthy answer. Okay, if they're not doing silly things. So that's what I'm going to talk to you about in these slides. Game theory was invented by a man named John Nash. There's a movie called A Beautiful Mind based on his life. If you're interested, you should watch it. It's very dramatized, but that makes for a good movie. And now let's talk about game theory itself. So it's all based on this very vague definition of something called a game. So it's not like us playing Candyland. It's us selling corn, too. So what is a game according to game theory? It's this. It's a strategic interaction between individuals in situations. Okay, so it's super vague, but that means it can talk about economic things just as well as it can talk about a board game, which is nice. Okay, so people are competing, individuals are competing in some kind of situation where there's something to obtain. Okay, games can be either cooperative or non-cooperative, and these definitions make sense, right? A cooperative game is when you're better off. You're better off working with somebody else. People are better off working together and forming groups. Alliances is another term that you see in game theory. Okay, so that's a cooperative game, one where it's better to play as a group, to get together with other people, like, I don't know, form a union or something. That's a cooperative game. They can also be non-cooperative, where it's impossible to form an alliance, or it's unfavored, which these are very interesting games that are non-cooperative. Yeah, if you end up in one of those, if you're playing one, that means if people end up working together ever, it's because they feel threatened, which is a funny definition, but that's a non-cooperative game. And so cooperative game theory kind of makes sense. That's kind of the games we have in our mind. It's all about fairness. Things should go well for everybody. It's very utilitarian. We'd like to make the most good for the most people. And non-cooperative game theory is like, I would like everything, please. It's like Monopoly. I would like to win. Okay? So that is the difference. And because the definition is so vague, a lot of things have come out of game theory that can be applied in a bunch of different fields, like economics, poli-sci, biology, philosophy. If you're a corn producer, you want to sell your goods, I guess that's technically economics, though. And so that is a thing. And a lot of algorithms have been created based on game theoretical concepts. And so people, they end up coming to a game theorist, spending lots of money on them, and writing a bunch of programs to solve for the optimal strategy to play their game, to sell their corn, for example. Okay? So that's interesting. You can assign, you can have mathematics apply to some very disparate topics in the same way. All right. So are there any questions about these ideas so far? These are just new terms. Has anybody learned about game theory before? Because I'm by no means the expert, but I will give you a flavor of it, that's for sure. All right. So yeah, the topic that I want to talk about first, which is, I think, everything that I wanted to say, is the standard non-cooperative game that everybody learns about when they learn about game theory. It's called the prisoner's dilemma. Okay? So let's go into that one. And it has a very interesting solution. We're going to solve the prisoner's dilemma. We're going to see what should happen. So here's the setup. There's a story involved. So you have two prisoners. They both committed a crime together, or supposedly committed a crime together, and they are put into two separate interrogation rooms. So they're not allowed to talk to each other, collude, or anything like that. And each of them separately is given the following options. Okay? Oops. So these are the options. You can either confess to the crime or not confess to the crime, as you can do, right? And so that means there are 4 possible outcomes based on what prisoner A does and prisoner B does. Okay, so let's make that grid of options. So here is prisoner A's choice and prisoner B's choice. So they can either confess to the crime or not confess, both of them, right? So you have the case where they both confess, where one confesses, the other does not confess. I'll say NC for not confess. And vice versa, like prisoner A can confess, but prisoner B does not confess. That means you're in this case. Or neither of them confess, and you're in this case. So you have 4 total options. And the interrogationers say, depending on this option, here's what's going to happen to you. If prisoner A confesses, but prisoner B does not confess, prisoner A is allowed to leave, but prisoner B is forced to stay there for 10 years. They get a 10-year sentence for lying, apparently. Okay? The outcome 2 is the opposite. If prisoner A doesn't confess, but prisoner B does, that means prisoner B is going to walk off for free. spend no time in prison, but prisoner A is going to spend 10 years there. Okay, so in both of those options, you have a bunch of time for somebody and no time for the other person. So here's the first option. If prisoner A does not confess, but prisoner B does, that means prisoner A gets 10 years, prisoner B gets 0 years. And the opposite's true for this one. If prisoner A confesses, but prisoner B does not confess, that means prisoner A gets 0 years and prisoner B gets 10 years. Okay? And, okay, if they both confess, you have that option. They say that you're each going to get 5 years in prison. Okay? So prisoner A is getting 5, prisoner B is getting 5, if they end up both confessing. And then the fourth outcome is a possibility. They say if you don't confess and your partner does not confess, then we've got nothing. The evidence is too circumstantial. That means you're both going to go away. You get to walk out free. So if they both don't confess, they get 0 years and they can all walk away. Okay? So the question is, the thing that game theory solves is, what should the prisoners do? Should they confess? Should they not confess? How should they play this game? It is a game, according to the definition. What are our thoughts? Obviously, they can't talk to each other, first of all. That's something we have to keep in mind. They're not allowed to talk to each other. They can't be like, okay, yes, let's just both not confess. They're both being told these rules separately. In a perfect world, we would like them to both not confess, right? That would be the best outcome for both of them. But game theory is going to show that's not what's really going to happen. And that's not intuitive, which is fun. Okay, so the question is, what should they do? What is the optimal outcome for some sense of optimal? Okay, so this is a very fun problem. If you haven't heard it before, I'm excited to show it to you. So, yeah, we want to figure out what should these prisoners do. And so this is one of the first key things that happen in game theory that was invented by John Nash. He came up with this concept of a Nash Equilibrium, okay, which is a, quote, optimal solution, an optimal way to play this game, okay? And it's going to go against some of our intuition, which is nice. So here's what a Nash Equilibrium means, okay? In order for your strategy to be a Nash Equilibrium, that means that, well, first of all, it is those strategies. That's what it means to be an equilibrium. It's tell the players how to play the game. It's a bunch of strategies, one for each player, that has the property that each player's choice is their best response to the choices of the other players. So they cannot play the game any better. That's what it means to be optimal, according to John Nash. Okay? That's what we want to find. We want to find these strategies. We want to tell the players how to play the game. That's going to end up in the best possible outcome for them. Okay? In response to the choices of the other players. So you have to consider what they might do. That's how a game works. So yeah, the key idea here is that prisoner A, this is a non-cooperative game, prisoner A doesn't know what prisoner B is going to do. So they have to play it safe. And there's a bunch of math that came along with this that's going to prove that they're going to want to play it safe. Okay, so a Nash equilibrium is just the mathematical way of playing it safe. That's the idea. Okay, so that's beautiful. Yeah, so another way to formalize a Nash equilibrium is to talk about, like, it's something that people would want to do even if nobody was watching, okay? It's a law that nobody would want to break even if there was no punishment for breaking it. It's like everybody's better off to be in this, to play with this strategy, okay? And one of those, a great example of a Nash equilibrium, is stoplights. When you come to a stoplight and it's red, you stop, right? Why do you stop? There isn't a cop usually. Why do you do it? Because you would like to live, right? That's mostly the answer. So, right, yeah, that's essentially a Nash equilibrium. So that's saying that, okay, I know that I'm not going to get caught. I'm probably, like, if I floor it, I'm probably going to get through the intersection unscathed. But it's very likely still, though, there's always that possibility that I'm going to hit somebody, somebody's going to hit me, I'm going to get hurt, they're going to get hurt. I would like to, preserve myself, and so I'm going to obey this law even though nobody's really watching, and I'm not going to get in trouble for running that red light. Okay? So that's essentially the idea. You think of how other people are going to play that game, and then you consider your best move. And apparently for stoplights, your best move is stopping. Stopping at the red. So Yeah, it's a self-enforcing law. And we're going to see a self-enforcing law happen with our prisoner's dilemma. So for the prisoners, what we'd like to do is calculate the average sentence in each outcome. So let's do that. Let's go back to prisoner A and prisoner B. You can either confess or not confess. And if you both confess, you both get 5 years. If one doesn't confess, they get 0 years, but the other gets 10. Oh, sorry, I did that backwards. This one is 10. This one is 0. And then this one is 0, because A confessed and B didn't. So B gets the 10. And then if neither of them confess, you get 0 and 0. Okay? So now, the question is, what is the average sentence in each outcome for each prisoner? And it's actually symmetric. So we can talk about this from the point of view of prisoner A or the point of view of prisoner B. It doesn't matter because when you draw a line, it's not really going to make sense. It's either like, do I want to consider all these possibilities for prisoner A confessing and prisoner B, or prisoner A confessing and all these possibilities for prisoner A not confessing? Or do I want to consider the options from prisoner B's perspective? If they confess, this could happen. Or if they don't confess, this could happen. It doesn't matter. It's symmetric. So let's just pretend we're thinking about this from the point of view of prisoner A. Okay? And so if prisoner A confesses, we don't know what B is going to do, but we have one of two options. And then if prisoner A does not confess, we don't know what's going to happen, but we'll know, we're not sure what B will do, but at least we know our options. Okay? So that's what's happening there. And so, yeah, from prisoner A's perspective, he could either confess or not confess. If he confesses, if he does not confess, and then we end up with average time in jail based on each outcome. Bloop. All right, so we're going to average together those things, and let's see what happens. So if prisoner A confesses, we have no control over B, but here is what's going to happen. What's the average amount of time in jail prisoner A might spend? So it's either 5 years or 0 years, right? So the average is 5 plus 0 over 2. That's 2.5 years spent in jail. And if prisoner A does not confess, he's either going to get 10 years or 0 years. The average time spent in jail there, 10 plus 0 over 2. That's 5. And so we just realized the optimal strategy for prisoner A, and also prisoner B, because it's symmetric, you can draw the boxes in the opposite way, horizontally. It's better for you to confess. Does that make sense to us? That seems unintuitive, but hopefully with the math, it kind of proved it a little bit more. It is the optimal strategy for each prisoner to confess because they cannot control their partner. Their average time spent in jail is smaller because of that. And so it's either 5 or 0, 5 or 0, which is always better for you. 2.5 is always better than 5 because you're not sure which case you're going to be in. It's like 50-50 chance of either. So it always makes the most sense to confess. It's crazy, which seems a bit paradoxical. Like if they could just both shut their mouths, they can both just walk out. But because it's non-cooperative, you can't really do that. Game theory, this Nash Equilibrium idea, explains away what's going to happen. It's always better for them to both confess. Okay, and that's the outcome. That's most likely what's going to happen. And I don't know enough about like criminal law to know, is this what usually happens? Is this a real thing? But most likely yes, because this is how the world apparently works, according to John Nash. Okay, so yeah, if you're ever in this situation, now you know to confess. Are there any questions about this topic? That's right. Yeah, just say no. We're not talking to the police. So, but I guess where's the fun in that, though? So yeah, that's the optimal strategy. It's like that 80s movie. The optimal strategy is to not play. Yeah.
In Jackbox, there's things similar to this.
think that is, yeah, this is this all over again. That's a great point. Everybody wants to fight rather than defend. And maybe there's an economics paper in that. That's cool research. So yeah, if we're happy with this, these are the topics that I wanted to talk about today. And I remembered to not forget that you have a test coming up. So am I still logged in? First of all, let's make sure of that. Otherwise, I can't click the button and have it work. There we go. Okay, cool. So you have a test coming up soon. We are in week 15. Week 16 is more lectures. Week 17 is, I'm just going to review for the final. And then week 18 is the finals week. Okay? Boop. So I'm not going to release the final because I haven't made it yet. But I'm going to release the final info page to you now. Okay? So if you go back to the syllabus, like I have told you before, this class has a specific time, which means we have a specific final time. Okay? We are stuck with a final on Monday of finals week. So you get to get it over with at least. It's going to be starting at 4 p.m., so class time, on Monday, May 16th, okay? So that is down here. Look at where we are and look at where we end, okay? So just everybody understands that's when our final is, right? 4 p.m. to 5:50 in this room on Monday, May 16th. And here is the final. I'm going to try and make it mostly like the midterm, so it's going to consist of an essay with a word limit, around the kind of limit that I gave you in the midterm. And then I'm also going to give you coding questions because I could finally ask you to write Python. I couldn't really ask you to write Scratch on the midterm. So prepare to write code in Python, like have idle open, and you'll just be pasting your answers into a Canvas text box, and I'll be giving you plenty of partial credit. Okay, so that is what's going to happen, and I'll be taking those questions from your programming assignments, from all the stuff I've been doing in class. So that's what I want you to study. Okay, there will be a lot of the turtle module, for example, because I'll ask you to draw some fancy pictures. That's what I'll have you do for some of the questions, for example. Okay, so yeah, the majority of the points will go towards the essay because I want to make sure you have time to write that. And yeah, everything goes. You're allowed to look at the slides, of course. You're allowed to use your notes. Look at the textbook if you have it. But the only person you can talk to is me, of course. Okay? But you're allowed to use the internet. Just don't chat to another human. All right? So that's what the final is going to be about. Those are the logistics. It's going to be 1 hour and 50 minutes is the time limit. That's just the standard time limit for a final. Okay? Any questions about that? All right, that's it.